Show by the principle of mathematical induction that for all n belonging to the set of natural number, the following is a true statement. Okay, let us begin. So first what we'll do, we are going to consider a statement denoted by P of n. So let P of n be the statement such that we have half multiplied to tangent of x over 2 added to, we have half 1 over 4 multiplied to tangent of x over 4. So this goes all the way up to the last term, which is given by 1 over 2 raised to the power of n multiplied to the tangent of x over 2 raised to the power of n. And this equals, this is a sum, the sum of the series equals to 1 over 2 raised to the power of n multiplied to cotangent of x over 2 raised to the power of n minus cotangent of x. So this is our mathematical statement, and we're going to denote it by statement number 1. Okay, now our goal will be to verify that this is a true statement regardless of any natural number that we choose. So what we'll do, first we are going to choose the natural number 1. So for n equals to 1, our statement is now going to become P of 1 such that we have, so since this is the nth term, we replace n value with 1. So that's going to give us 1 over 2 multiplied to tangent of x over 2. And this is going to be equals to the expression on the right hand side, where we replace n with 1, we get half cotangent of x over 2 minus cotangent of x. However, we see that the left hand side is not equals to right hand side, which means that we'll need to manipulate the expression on the right hand side to make it equals to the left hand side. So here what we'll do, let's take 1/2 times tangent of x over 2 as the common factor. So if we take half tangent of x over 2 as the common factor, that means in the first term we will be left with cotangent squared x over 2 minus the second term will become cotangent of x multiplied to cotangent of x over 2, and we also have a factor 2 multiplied to it. Okay, now we'll have to work with the expression within the parentheses. So here we're going to take the half angle formula. So we know that if we have tangent of angle x, so this is simply given by 2 times the tangent of angle x over 2 divided by 1 minus tangent squared x over 2. Now we know that the tangent and the cotangent function are reciprocal of each other. So when we take the reciprocal, that means we are going to get cotangent of x, and this is going to be equals to cotangent squared x over 2 minus 1 divided by 2 times cotangent of x over 2. Now when we cross multiply, we simply get 2 times cotangent of x times cotangent of x over 2. That means we can replace the second term. So let's write down half. We have tangent of x over 2. This is going to get multiplied to cotangent squared x over 2. So in place of 2 times cotangent of x times cotangent of x over 2, what we can do is we can replace it with cotangent squared x over 2 minus 1. Fine. So that means when we simplify cotangent squared x over 2, that gets cancelled out, and this is going to leave us with half tangent of x over 2. So here we have been successful in showing that the left hand side equals the right hand side. So this simply means that the statement P of 1, this is going to be a true statement. Fine. Now that we have shown that P of 1 is true, we have to show that it is equally true for other natural number. What we'll do, we'll consider and we'll make an assumption here. So here we will assume that let P of m, let's say this is a true statement. Let this be true. Now what is P of m? We already have the statement P of n. So P of m is going to be given by, so here we have half multiplied to tangent of x over 2. So that's the first term. Added to it 1 over 4 multiplied to tangent of x over 4. So this goes all the way up to the last term, which is given by 1 over 2 raised to the power of m multiplied to tangent of x divided by 2 raised to the power of m. And this is going to be equals to, we have 1 over 2 raised to the power of m multiplied to cotangent of x over 2 raised to the power of m minus cotangent of x. So this is the statement P of m, and we are considering it to be a true statement. So let's call it statement number 2. Now using this statement, our goal will be to verify that the statement P of m plus 1, this is true as well. This is also true. This is our goal. Now what is m plus 1 here? M plus 1 is simply the consecutive term to that of m. Fine. How do we show that P of m plus 1 is true? But before that, let's try to write down the statement P of m plus 1. So P of m plus 1, this statement is simply, we take the first term, which is half tangent of x over 2, added to the second term, which is 1 over 4 multiplied to tangent of x over 4. This goes all the way up to the second last term, which will be given by 1 over 2 raised to the power of m multiplied to tangent of x over 2 raised to the power of m. Now this is the second last term. To get the last term, what we'll have to do, we'll have to replace m with m plus 1. So we get 1 over 2 raised to the power of m plus 1 multiplied to tangent of x divided by 2 raised to the power of m plus 1. Similarly, on the right hand side of statement number 2, wherever we see m, we'll have to replace with m plus 1, where 1 over 2 raised to the power of m plus 1 multiplied to cotangent of x divided by 2 raised to the power of m plus 1 minus cotangent of x. Now this is the statement P of m plus 1. However, we do not know if it is true or not. Our goal will be to verify that it is indeed true. So how should we proceed? So let's take the left hand side of P of m plus 1. Now in the left hand side, what we'll do, we'll consider the first term added all the way up to second last term, and we can replace that with the right hand side of statement number 2, because we have already considered statement number 2 to be a correct statement. So that means we now have on the left hand side, we have 1 over 2 raised to the power of m multiplied to cotangent of x over 2 raised to the power of m minus cotangent of x. So this is the sum of the first term all the way up to the second last term, and then we have the last term given by 1 over 2 raised to the power of m plus 1 multiplied to tangent of x over 2 raised to the power of m plus 1. Okay, so our goal will be to combine these terms. Now we need negative cotangent of x on the right hand side as well, so we're not going to touch the second term. We're only going to combine the first and the third term. So let's rewrite them together. So we have 1 over 2 raised to the power of m multiplied to cotangent of x over 2 raised to the power of m added to 1 over 2 raised to the power of m plus 1 multiplied to tangent of x over 2 raised to the power of m plus 1. Fine. And we have negative cotangent of x. Fine. Now we know that cotangent function is the reciprocal of the tangent function. So what we'll do, we'll take the reciprocal of the cotangent in the first term and convert it to a tangent function such that we get 1 divided by, we have 2 raised to the power of m. This is going to get multiplied with tangent of x over 2 raised to the power of m. Fine. And then we have the rest of the terms. Now what we'll do, we'll do some manipulation here. We're going to multiply the numerator with 2, and we'll have to multiply the denominator with 2 as well. Now the angle of tangent function in the denominator, that's x over 2 raised to the power of m. So what we'll do, we're going to multiply the numerator with 2 and the denominator with 2 as well. So this is done such that we have 2 raised to the power of m plus 1 in the denominator, because we need 2 raised to the power of m plus 1. This will become evident in a moment. So here we have 2 divided by, now 2 times 2 raised to the power of m, that is simply 2 raised to the power of m plus 1 multiplied to tangent of, now we have 2 times x divided by 2 raised to the power of m plus 1. Fine, and then we have the rest of the terms. Now, the whole reason of multiplying the angle of tangent function with 2 in the numerator and the denominator is because we're going to apply a formula here. We have a formula. Whenever we have tangent of 2 times some angle theta, this is simply given by 2 times tangent of that same angle theta divided by 1 minus tangent squared theta, which means that in our case, what we'll have now is we have 2 in the numerator divided by 2 raised to the power of m plus 1. Now we're going to expand this tangent function. So that means this is going to give us 2 multiplied to tangent of, we have to take half of the angle of tangent, which is 2x over 2m plus 1. Taking the half of the angle is simply going to give us x over 2 raised to the power of m plus 1 whole divided by 1 minus tangent squared, so we need x divided by 2 raised to the power of m plus 1, right? And we have the rest of the two terms. Now we can factor out this 2 from the numerator and the denominator, and we will simplify the first term. So this entire denominator portion is going to go to the numerator to give us 1 minus tangent squared. We have x divided by 2 raised to the power of m plus 1. Fine. And then in the denominator, we have 2 raised to the power of m plus 1 multiplied to tangent of x divided by 2 raised to the power of m plus 1. And then we have the rest of the two terms. So now what we'll do, we're going to combine the first and the second term. Now from each of the two terms, what we can do is we can take 1 over 2 raised to the power of m plus 1 as the common factor, such that for the first term we have 1 minus tangent squared. We have x divided by 2 raised to the power of m plus 1 whole divided by, we have tangent of the angle x divided by 2 raised to the power of m plus 1 added to, so here we have tangent of x over 2 raised to the power of m plus 1. Fine. And we have the remaining term, which is negative cotangent of x. Fine. So this is going to be equals to 1 over 2 raised to the power of m plus 1. We can combine them, the common denominator. So that's going to be tangent of x divided by 2 raised to the power of m plus 1. Fine. In the numerator, we have 1 minus tangent squared of the angle x over 2 raised to the power of m plus 1 plus. So this denominator is going to get multiplied with the numerator to give us tangent squared x over 2 raised to the power of m plus 1. And we have the remaining term, which is negative cotangent of x. So luckily for us, the second term and the third term cancels out, and that leaves us with 1 over 2 raised to the power of m plus 1 multiplied to, we have 1 over tangent of, let's write it down, 1 over tangent of x divided by 2 raised to the power of m plus 1 minus cotangent of x. So finally what we can do, we can take the tangent to the numerator by taking the reciprocal. So we have 1 over 2 raised to the power of m plus 1 multiplied to the cotangent of x divided by 2 raised to the power of m plus 1 minus cotangent of x, and this is the expression on the right hand side. This is what we are needed to show. So let's check it out one more time. So we needed to show 1 over 2 raised to the power of m plus 1 multiplied to cotangent of x over 2 raised to the power of m plus 1 minus cotangent of x. So here we have successfully showed here that the left hand side equals the right hand side. Now that the left hand side equals the right hand side, it tells us that the statement p of m plus 1 is true. So p of m plus 1 is true. And what we have done, so we started out by first considering that the statement p of m, this is a true statement, right? And with the help of this statement, we are able to show that p of m plus 1 is also a true statement. we are successfully able to show that P of n plus 1 is also a true statement. If this is true, then by the principle of mathematical induction, we can finally say that the original statement which we consider, that is P of n, the P of n is also going to be a true statement, and now it's going to be true for all values of n belonging to the set of natural number. That means any natural number that we pick up, the statement P of n, which we considered P of n, is always going to be a true statement, hence proved.